Here we're going to be looking at chi-squared. So this is one of the statistical tests you need to know in terms of your A-levels, specifically to do with your genetics. So we need to think about what is chi-squared. Now, it's a statistical test that allows us to actually compare what we would expect our results to show and what they actually showed. So it's to see if there's a significant difference between them. So if there is a significant difference between them, it means that there's been something that has affected our results. So something has happened to actually affect our results. Now, in terms of genetics, we don't want to go and see a significant difference between what we would expect in terms of an offspring's phenotype and what we actually observed. So when we actually want to go and carry our chi-squared out in terms of our genetics, we need to go and actually think about how we would actually go and get our expected results. So to get our expected results, we need to actually go and carry out our genetic cross. So we need to go and do a genetic diagram to go and find out what the ratio of the expected phenotypes would be. Now, we can actually go and see that the observed results normally always differ. Okay, we're not going to have an exact 3:1 ratio or 9:3 to 3:1. It will never be exactly that. Now, this is due to a number of chance events. So chance events could be fertilization. So it's completely random which X or Y sperm fertilizes the egg. They each have an equal chance of fertilizing it. We also have our independent assortment in meiosis, and we also have crossing over and the formation of our chiasmata. So these all influence the resulting phenotype as well. So when we're thinking of our chi-squared, there's a specific equation that we need to know. So it is the sum of the observed result minus the expected result squared divided by the expected result. Now, when we're actually thinking of this, we need to go and carry out this part here for each of our phenotypes. This part here is what we're doing at the end. So we're adding these up at the end. So we're adding all of these numerical values at the end to give us the total of our chi-squared. Now, a little hint here is the smaller the value of our chi-squared, the more certain we can be that the difference is down to chance. Okay, so the difference is down to chance, and the difference is not significant. So we say it's not significant, it is down to chance, which means that we can go and accept a null hypothesis. So our null hypothesis is that any difference that we are observing is down to chance. So here, if we wanted to actually go and look at an example of one of our crosses, or if we wanted to go and cross some gerbils to go and see the resulting colour of their fur, we want to go and see, we use the chi-squared test to go and see if the difference in the actual offspring is down to chance, or if there is a significant difference, and if two genes are actually linked. So if two genes are actually linked and giving one of those alleles a prevalence in the actual resulting population. So if we have a look here, we have our dominant B here, which coding for black fur, and we have a small b here, which codes for brown fur. Now, in a cross of two heterozygous gerbils, so we know they have a capital B, a dominant B, and a recessive B, 29 black-coated gerbils were produced and 7 brown. So we need to go and do our genetic cross first to go and see if the results, well, we need to go and calculate the results for the actual ratio before we can actually go and run our chi-squared. So this is what we would have. So we need to go and think about the phenotypes of our parents. So we know we've got black fur, because they are heterozygous. The genotypes would be our dominant B, recessive B, because we know they're heterozygous, our gametes should be in circles. So dominant, recessive, dominant, recessive. We carry out our Punnett square. So here we have dominant homozygous, 2 heterozygous, and one recessive. So just one recessive. We need to go and put that into a ratio. So we've got 1 to 2 to 1. Now, if we actually think of what's happening in terms of the phenotypes for these, we can see that we have a 3 black fur to 1 brown fur ratio. So the ratio that we have is 3 to 1. Now we need to go and think about how we can enter this into our chi-squared. Okay, so we know we have a 3 black fur to 1 brown fur ratio. So we observed 29 black coated and 7 brown coated. We need to now use our chi-squared equation here, so observed minus our expected squared divided by expected, to actually calculate whether the variation is due to chance or not. So we need to have this in a table form. So here, this is the simplest way to help you remember. So we have the observed. So here, there's 29 black fur, 7 brown. The expected, though, we had 27 black fur and 9 brown fur. So we've taken our 3 to 1. So we need to go and add up our 29 and 7, which gives us 36. So it's 36 in total. We now need to go and have our ratio for that. So we do 36 divided by 4. So we know 1 is 9 and 3 times 9 is 27. So this gives us what numbers we should expect to see. Then we put these numbers into our equation. So 29, which is our observed, minus 27, which is our expected, squared, divided by 27, which is our expected. This is going to give us 0.15. Again, we have our observed, which is 7, minus 9, which is the expected number, squared, divided by 9, which is our expected. This gives us 0.44. So we add these numbers up now, and that is going to give us 0.59. Now, with that, we have our chi-squared, but we also then need to use our probability table. Okay. So our probability table helps us to actually go and decide whether the probability of chance is great or not. Okay, so we compare our chi-squared to the critical value. Now in biology, we have a specific critical value, but we need to think about our degrees of freedom first. So the degrees of freedom are the number of categories you have. So we only had 2, we had black and brown, minus 1. So that means we have 1 degree of freedom. Now in terms of our probability, the critical value that we use in biology is 0.05. Now we have our chi-squared, which is 0.59. We need to go and follow our table down from the critical value and along from our degrees of freedom. This gives us 3.84. Anything less than this shows that the probability of our results being different due to chance is valid. Okay, so our differences are just due to chance. So here we can go and accept our null hypothesis, which is that the differences are due to chance, and that we can go and accept it. So it fits the pattern. So here we're going to have a look at a past paper question. So we're looking at red and yellow flowers. So we need to go and carry out a cross and obtain 18 plants, all that have red flowers. So we need to go and think of what the parents, their phenotype would be. So we'd have to have a red parent, and we also need to go and have a yellow parent. Now in terms of their genotypes, we need to go and have our red parent as dominant homozygous and our yellow is our homozygous recessive. Their genotypes, their gametes, sorry, are going to be R, both dominant, and then we have R recessive. Then we need to go and think about our Punnett square. So in terms of our Punnett square, we can see here that all of the offspring are going to be red. So the genotype is all heterozygous. The phenotype is all red. So we need to cross two of these. So our parents are going to be red and red. The genotypes are going to be heterozygous. Their gametes are going to be dominant, then recessive. And if we do our cross, we can see here a dominant, homozygous, heterozygous, heterozygous, homozygous, recessive. So we're going to have, in terms of our genotypes, we're going to have a 1 homozygous dominant to 2 heterozygous to 1 homozygous recessive. But our phenotypes are going to be our 3 red to our 1 yellow. Okay. So if we now think we've got a 3-to-1 ratio, we can have a look at what we'd enter into our chi-squared. So our observed, we've got 17 red, 3 yellow. So we have a total of 20. So we've got a total of 20 flowers. So we have a 3-to-1 ratio, so we need to go and have a 3-to-1 ratio in terms of 20. So we should have 15 red, 5 yellow. Okay, so it's a 3-to-1 ratio. We put this into our equation for our chi-squared, so observed minus our expected squared divided by the expected. So for our red, we're going to have 0.27. For our yellow, we're going to have 0.8. We add 0.27 and 0.8 together to give 1.07. So now we need to go and think about what this would be in terms of our chi-squared. So here we know our chi-squared is 1.07. Our degrees of freedom is 2 minus 1, which gives us 1. Now our critical value reads as 3.84. So we know that our degrees of freedom, 1.07, is less than 3.84. So our results do not differ significantly from what we would actually expect, which means we can accept our null hypothesis.